Hey everybody, and welcome back to Algebra 2 Online. So the plan for today is just go through some problems from our Chapter 4 Quadratics unit. And all of these are just good examples to know for the whole unit. Really just going to review a bunch of different things from the start of our quadratics unit to the end here. So one of the first things we did was we talked about the different forms of quadratics. And you should definitely feel comfortable with like moving between the different forms. If I have, this is a standard form one, right? And if I was asked to put it into vertex and factored form, the factored form is honestly a little easier because all you have to do is factor it. And if you're going to factor this one, you know it has to start with like a 2x and an x to multiply to 2x squared. And you have to multiply to 5 and add to 11 once you do out all the like distributions in here. And you can play around with it. There's really only either it's going to be a 5 here and a 1 here, or a 1 here and a 5 here. And you could just try it, but if you put the 1 here and the 5 here, then you'll have it, right? Because this is 10x, this is just 1x, and that adds to 11. I think I'll delete that actually. So this would be my factored form. For vertex, you'll have to do a little bit more work because you actually got to find the vertex. So I'm going to start with finding the line of symmetry. If you plug in b and a, you get negative 11 over 4. And then that's the x value of the vertex, which will be used. But we need the y value too. We need like the full vertex, right? So we got to plug in the x value for all the different x's here. And if you just crank through that algebra, you can do it on a calculator or something, you get negative 10.125. And so we're basically there because we just got to put things in the right form now. So we know, kind of generally speaking, there's like a scale factor, and then I guess I should do x there. And then there's a number that goes here and a number that goes here. These two numbers are the vertex, and it's always the opposite of this, and then this one is just like the straight vertical shift value. And the a value has to match all these, right? These all have to be the same. So so basically we can just stick, we got this 2 here, that has to go in there. We had the vertical shift of negative 10.125, and that's going to go in right here. And then we've got this value right here is my, my left-right shift, my x value of the vertex. And the weird thing is with those, you always have to put it in with the opposite sign. So it's positive 11 over 4 right there. And I guarantee you if you go and use some sort of graphing program, if you plug this in or the original one up here, all of those would give you the exact same graph, the exact same quadratic. All right, another important thing from this unit is just our systems of nonlinear inequalities. So really we did some of this, honestly, when we were reviewing some Algebra 1 stuff too at the beginning, but there's, a little more we did with graphing quadratics, so it's good to kind of go through something like this too. So this is vertex form quadratic, right? And so if we were going to graph this thing, we'd be shifted over 2 and then up 4, right there is the vertex. And then you can always just plug in an easy kind of point. So if I do, an easy point could be like 0 or something. So negative 0 minus 2 squared plus 4. This is going to be negative 4 plus 4 is 0. And so if we plug in 0, we get 0. So we're right there. And then based on symmetry, if we flip over the line of symmetry, right, we would be also at 0 over at x equals 4. This is a solid curve, right, because it's an equal to inequality. So that's like the first one. We haven't shaded yet, but I think I'll just shade at the end here. So for this one, this is a line, right? It's a point slope line, you know, based on this -1 and this -2. The point is over at 1, 2. And then it's got a slope of -3. So just down 1, 2, 3 over 1. Let's just do another one, down 1, 2, 3 over 1. This one is a dotted line like that because it's just a less than. Then last but not least, we got a step function, just a floor function here, and it's kind of just like a normal floor function, so there, but this time it's stepping down, not up, because it's a negative in front. It like flips, it does a vertical flip there. Let's just do one more, so here, and then there. And then for shading, so we're shading above the quadratic, so like up here, above that quadratic, below the line, so everything below this line, and then below the step function, so below that step function. And so if you put that all together, basically you have to be, you know, somewhere kind of over here. So you're outside that quadratic, above that quadratic, but you're below the other two things there, the step function and the line. So this is another very important thing just from this unit. You'll see some stuff definitely with graphing quadratics and systems of inequalities. All right, this is just a kind of good concept question. So it says, suppose a quadratic function, just kind of a general one there, satisfies f of -2 equals 0 and negative b over 2a equals 1. And given this, solve f of x equals 0. So, solve, what it's basically saying is find the roots of the quadratic, right? If the quadratic is set equals 0, we're just saying what are the roots of this thing. And if you think about what you're getting here, f of -2 equals 0 is one of the roots, right? So I know that if I draw a little picture here, over at -2, I got one of the roots right there, right? If you think about what this is the line of symmetry, right? So that part right there tells me that at 1, right, I have a line of symmetry. And it wants the roots of the quadratic. I know one of them. I'm like halfway done with the problem, honestly. If you have a line of symmetry and one root, though, you should be able to get the other one and solve this thing. So you basically just need to think about how far you went from the line of symmetry over. So we go from 1, we go over to the left 1, 2, 3 to get to -2. So we have to use symmetry and go the other way. So from 1, we go to 2, 3, and then over to 4. Would be going 3 in that direction. So this means that 4 has to be the other root. We don't know, does the graph go like this, right? We don't know, does it do something like that? Like that kind of stuff is not clear. It might be like a really, really far one and go like way down there and then come back up or something like that. There's all sorts of cases. There's infinitely many quadratics that go through those two roots. But the question was really like, you know, what are the roots for the quadratic? And the roots end up being both f of -2 equals 0 and f of 4 equals 0. Remember that you always should get two answers for a quadratic. They might be imaginary roots or something like that, but that's totally fine. But you should never be answering one thing for a roots kind of question with a quadratic. You might just have one root repeated, but you should always even still list the repeated root twice. All right. So we did some of these. There was a video I made that was basically the same thing but different numbers. But they're really good problems to make sure that you kind of understand. So I want you to write down a quadratic inequality which goes through this point and has a solution of -1 is less than x, which is less than 4. So if you have a quadratic inequality and like a solution like this, you know from doing a lot of these quadratic inequalities that those are like the roots of the quadratic. So it kind of makes sense to base it off of kind of the general roots sort of setup. So we've got like x plus 1, x minus 4, because we know the roots are negative 1 and 4, so we do the opposite numbers in here. We don't know what this is, right? We can never assume that that's just a 1. Sometimes it is, right? But a lot of times it's going to be something else. But that's where this point can help us, right? So we can just plug in this x and this y, and then we should be able to solve for that. So if we do that, we've got 82 there, and then we'll put in negative 72, and then, so all I did there is I plugged in x and y, right? And if you solve that thing out, you get 82 equals, I think this is 5,396 times a. So if you divide that over, a works out to be 5,396 over 80. Nope, that's not how it works. Sorry, 82 over 5,396. And then now you know the quadratic, you know the roots, and you just got to think about how you would get an and kind of answer. So we know that like the quadratic we're working with is like 82 over 5,396 times x plus 1 times x minus 4. And if we think about that like in a picture, right, we've got negative 1 there, we've got 4 there. This scalar is positive, so it's doing something like that, right? And we have an answer that says the solution is anything between the roots negative 1 and 4. So in order to do that, we must be talking about the part that's below 0. So the answer has to, like the quadratic inequality has to be, you know, the quadratic less than 0, right? Because that would describe this part down here that matches with my negative 1 is less than x, which is less than 4. So that would be the quadratic inequality that guarantees to go through this point and has this solution. Another very important thing related to quadratics are some application problems, like with, for example, here, this is about projectile motion. So you've got an object is thrown upwards at time equals 0 with velocity. This is just kind of standard notation. We would say v sub 0 or v naught is how we say it. And it's basically a way to say like initial velocity. So the 0 there is like a subscript as part of the variable. So like v sub 0 is different than like v sub 1. But it's basically saying like the initial velocity. And from an initial height of s sub 0 or s naught above the ground, and its height at time t is given by this thing. So that is just like given information, right? Then it says, suppose a diver jumps from a springboard 15 meters above the surface of a pool with an upward velocity of 6.5 meters per second. So if we combine these two things, right, we basically have an equation, h of t, right, equals negative 5t squared. And then in this scenario, right, I have a upwards velocity of 6.5 meters per second. That's my velocity, right? So I got plus 6.5 right there, t. And then the initial height is this last thing, right? And that is, it says the diver jumps from a springboard of 15 meters above the surface of a pool. So that's my like initial height is 15. That's basically then the quadratic that I'm working with. And I can kind of draw a picture here. So maybe we'll even, so we got water down here, right? And there's like the diving board is like up here, right? So this is my beautiful ladder. And then the idea is your person is up here, starting 15 feet off the deck. And they're going to dive, and they're going to like model a quadratic, and then they're going to land in the water, right? That's like that question. Or that's like the setup, I guess, for this question. So the first part says, when does the diver fall past the springboard on the way down? So this is a when question. So remember that, you know, a lot of application problems, the x-axis is, so maybe we'll kind of keep the colors here. So time is the x-axis, and then the you know, the y-axis right there is height, or h here. So what this is really asking us here is, you know, what time. So we want to know when they fall past the diving board, the springboard. So right about here, let's say, right, that's about where they would start falling past the springboard. So the question is basically, what time is that, right there? When, right, does that happen? When do you get to the exact same, you know, height as the springboard? I'm going to erase that. So we know the height of the springboard is 15, right? So we could just go ahead and do, set the quadratic equal to 15, because that is when you would be at this height, right? That's the height. I'm just setting it equal to 15. And then we can just go ahead and solve this thing. So these cancel, negative 5t squared plus 6.5t now equals 0. It's a really nice factoring one. You can take a t out. And then you get, oops, I dropped a t in there. And then we have like two roots here, right? So we know this root makes sense because t equals 0 is one of the times that we're at 15. So one of them is t equals 0. T equals 0. And then that's the one related to this. And then this other one, I'll do it in green. If you set that equal to 0, that's really the one that matters for this question. And that would work out to t equals 1.3, basically 1.3 repeating, I guess. But and that would be the one that I want, because we know t equals 0 is when you're at that height of 15, and this is when you fall past it. All right, so for this last part, it's saying when will the diver hit the water, right? And the water down here is just t equals 0, right? So if we take the quadratic and we set it equal to just 0, basically we're just finding the roots. We would get the height. And pretty much as soon as I see decimals in a quadratic like this, I just think quadratic formula. And so I'll just I'll just write down the quadratic formula stuff here. And you just crank through that and you'll get the roots. And you don't want, you know, one of the roots is going to be some negative number over here, right? Because like this curve would kind of keep going. And like you don't obviously want that root because that makes no sense. So when we do the quadratic formula, we would expect a negative root and a positive root. And the positive root is when the diver will hit the water. All right, so that's the quadratic formula. And then like I said, we don't want the negative root. Doesn't make any sense. And so we would want, you know, this one. And the problem is in seconds. So this is like 2.5 seconds would be the time when the diver hits the surface of the water. It's right there. All right, just one more kind of problem, and it's kind of different, but it's a good one to see. So this is another just nonlinear system problem, but it's a system of equations, and it's kind of good geometry review too. So we haven't really seen one of these this year in a while, or really at all. But this is a circle, right? And it's a circle, it's centered at the origin, and it's got a radius of the square root of 27, right? So we've got like this kind of picture, roughly. So that is the square root of 27. And then this, right, is a quadratic. And I would personally rewrite the quadratic, solve for y. So I would do like x squared minus 3 equals 2y. So I'd like switch the 2y and the 3 on those sides. And then if you divide by 2, x squared over 2 minus 3 halves is y, right? And that quadratic, like very roughly, would look, something like this. It's like a quadratic that's shifted down 3 halves, and it's got a vertical like squish or compression factor of 1/2. But this is a system of equations, so I would not, graph it to solve it. But I just wanted to kind of show you roughly what it looks like, because it kind of gives you an idea that we should basically be expecting 2 solutions. And so now we'll just do that with the algebra and figure out what those 2 are. So if you got something like this, you can actually just go, you can basically do like substitution. You can honestly do elimination if you want to, because you could eliminate x squared there. But I think I'll just do substitution. But I'm going to do it kind of in a weird way, I guess. So I'm going to solve for x squared here, and then plug that in up here, and then I'll have something in terms of y that I can solve. So the quadratic solved for x squared, right, would be x squared equals 3 plus 2y. So if I take that and I'm going to go plug it in right there, I would get 3 plus 2y plus y squared equals 27. And then now I've got a quadratic that I can just find the roots for. So I'm going to put everything on one side. So this thing factor is pretty nice. You can multiply to negative 24 and add to 2 if you use 6 and 4, right? And specifically if you use positive 6 and negative 4. And so then my roots would be y equals negative 6 and positive 4. And those are just the, the x values of, the y values of the y values of like the solution, right? And then we just need to get the x values. So we can go back up here and we can plug in what we know. So x squared equals 3. There's basically like, we'll call this like case 1. 3 plus 2 times, let's do the negative 6, right? So x squared equals negative 9. And then x would be plus or minus 3i for this, right? And then there's like a case 2 where you're plugging in the other value 4. So x squared would equal 3 plus 2 times 4. X squared would then equal 8, 9, 10, 11. So x would equal plus or minus root 11. So if we kind of sum all this up here and just organize this a little bit, we know that there are 2 real intersection points, and then there's like 2 other imaginary intersection points. So we have one of the solutions being square root of 11 comma 4. That's like, actually that one's right here roughly. And then we have negative square root of 11 comma 4. that one is right there. And then there is another intersection point and axis we don't see, 3i comma negative 6, and then negative 3i comma negative 6. And really what these two are doing, if you kind of pull this graph like out of the paper, it's going to kind of create this like curve and actually intersect the circle like down here basically. And it intersects in the imaginary axis. You can see that other intersection point. But, you know, and this is the kind of thing where depending on the problem and, you know, engineering or physics or math, whatever you're studying, these might be important to you, or maybe you just want to know these ones. It totally depends on the problem. But technically, if you want to list all intersections of that parabola and that circle, you would get these 4 different points. And 2 we can see, you know, this is the 2 real ones we can see. And then this quadratic, really, if you like pulled it out of the paper, it is going to technically cross this down here again. And that's this intersection.